Please go ahead, Huang.
Okay, thank you for your kind introduction. Also, thanks for Professor Wang's invitation. My name is Tian Huang, and I'm a postdoc from Professor Steve Granick's group. And I'm happy to be here to share our recent work. So today I'm going to talk about the molecular diffusivity and during the chemical reaction. So my title is Molecules, the Ultimate Nanomotor. So also known as if you can't annoy someone with your experiments, there is no point in doing them. So my postdoc life has been very interesting. So almost half of my time is kind of like fighting with others. So, because our boosted diffusion work has got a lot of attention. And sometimes when a new result turns out, so it's always coming along with debates. So of course, these debates can help us to understand more about the question. And yes, so we received a technical comment which claim that no enhanced or boosted diffusion, and a more louder voice about no evidence for the active propulsion. So actually there's several comments, and so we need to answer what they ask. So has anyone heard the story about David and Goliath before? Okay, so the Goliath is a very strong giant. So he has very good armor and very good weapons. So, but he is arrogant, and he keeps attacking the country of the David. And so the David is a young boy, and actually he is a shepherd, but he has great courage and faith. So although he has no good armor, but he has very good aim with his slingshot. So with great courage inside, he accepted the challenging from the Goliath, and you can guess the ending. So in the first technical comment, so they doubted about the gradient sequences we used. So they mentioned that the use of monotonically increasing gradient can produce erroneous diffusion coefficients. And they show that no boosted mobility when the shuffled gradient applied. So this is one of the figures from the technical comment, and they tried 3 different gradient sequences. So you can see with the increasing gradient applied, the diffusion coefficient shows this decreasing tendency, and with the decreasing gradients applied, they show this increased tendency of the diffusion coefficient. And then if they apply this shuffled gradient, also called random sequence, and there is no change on the diffusion coefficient. So they thought, so our observed enhanced diffusion is caused by the merriment artifact. But in our reply to this technical comment, no gradient dependency was found. So we were curious why, and we want to know what happens in this problem. So finally, we got the data of these technical comments. So these comments was written by 2 groups together. So you can see actually these 2 groups data is conflict with each other. And also they only show part of the reaction data. So the group 1, you can see with the random sequence, the diffusion coefficient has no change. But this group 2's data, actually they show this decreased tendency. And if you analyze more the data, this decreasing tendency is almost the same as our data. So, and we found this group 1's the data, the NMR curves, the signal to noise ratio is very small, but this group 2's data is extremely good. It's excellent, and also this group 2 data you can see with these 3 different gradient sequence, they show this same decrease tendency, and this is same to our data. So, but this is different from this technical comment. So we don't know how these 2 groups can work together. So after this, so they try to find some other problems in our boosted diffusion work. So they mentioned they carefully reanalyzed the same data and find no evidence of this boosted mobility. So as this figure shows, so this is about how you choose the control value, like the baseline value, and how you normalize the data. So for this one, I would say this is a very important point, actually. And we think more deeply about this question, and we found there are reaction intermediates involved in the reaction. And these reaction intermediates will affect the molecular diffusivity. So now I'd like to introduce the reaction we studied. So it called the copper-catalyzed azide-alkyne cycladdition reaction. So this reaction is a classic click reaction, and it was discovered by Schappers, Fokin, and Meadow around 20 years ago. And it's widely used in many fields. So this reaction, it can happen at the room temperature and at the water and in the water, and also with a very high production yield. So there are 2 reactants, alkyne and azide, and the catalyst is the copper 1, the cuprous ions, which is reduced from the copper sulfate by this ascorbate, and this is the product. This is the reported reaction mechanism cycle. So you can see it's not a simple one-step reaction. So there are many steps involved in this reaction. So the alkyne reactant first form this 1 copper complex, and then it forms this 2 copper alkyne complex via this pi bond, and then this 2 copper alkyne complex react with another reactant azide. And after this several rapid transition states, it forms this triazolide complex. So this is an intermediate complex of the product. And with the leave of this copper catalyst, the pure product was produced. And so these several intermediate complex can be isolated, which already are reported in the literatures. So that means this lifetime of these several intermediates is relatively long and stable. And we use this nuclear magnetic resonance method to measure the diffusion coefficient of these molecules. And why we choose this method, one reason is because this reaction will quench the fluorescence of the molecule. And the other reason is because some people say there are artifacts in the FCS. This is the fluorescence correlation spectroscopy, and people say you cannot believe the FCS. So we use this pulse field gradient NMR method to measure the diffusion coefficient of the molecules. So the main difference from the common NMR experiments is this gradient. And so the magnetic field intensity along the z-axis of the sample is different. So by using this gradient, the molecules can be spatially labeled. So according to this statistical Tanner equation, so one can calculate the diffusion coefficient of the molecules. So this is the the I is the observed intensity, and the I0 is the intensity without applying the gradients. So this gamma is the gyro magnetic ratio, and the G is the gradient strength, and this small delta is the gradient length, and big delta is the diffusion delay time. So during the measurements, this gamma and the small delta and big delta are fixed. So we only change this gradient strength. So normally we change like we have 16 gradient strengths. So then we can get a series of attenuated intensities, and then we can fitting this intensity versus this paramagnetic gradient parameter, and the slope is the minus d. So from this slope, we can get the diffusion coefficient we want. So that's how we get the diffusion coefficient of the molecules. And so let's see the first reactant alkyne. So this reactant, it has two kinds of protons, this terminal proton and this methylene protons. We measured the intensity ratio of these two protons. So for without reaction happens, the intensity ratio of this proton 2 and proton 1 is nearly 2. So because here it has two protons and here only one protons. But we found during the reaction happens, this intensity ratio is not exactly 2. It's larger than 2, and it also keep changing during the reaction. So this is because the intermediate complex formation. So you can see in this one copper alkyne complex, the two protons and this one proton still in this alkyne reactant. But in this two copper alkyne complex, this terminal proton is replaced by this copper catalyst. So, and we know how much we added into the reaction, this alkyne concentration. So we can calculate the concentration of this two copper alkyne complex, which is the real catalytically active complex. And we measured this proton 2 and proton 1, so we can get the diffusion coefficient of these two proton, these two kinds of proton. And we tried several different stoichiometric ratios of two reactants. So this one is the azide axis, and this one is the alkyne axis. So we can see this this decreased tendency of these two protons, which is almost the same as our previous result. But yes, this absolute value is smaller than this control. This control means without reaction, without the copper sulfate. It's a mixture of alkyne and azide and ascorbate. So this is because the intermediate formation, because the intermediate complex, the size is larger than this pure alkyne reactant. So they show this smaller absolute value than without reaction. But as we mentioned, so the two copper alkyne complex is the real active complex. So from the concentration of these two copper alkyne complex and this diffusion coefficient, we can calculate the diffusion coefficient of these two copper alkyne complex. So this is from several independent measurements, and we can see for these two cases, both we can observe the boosted diffusion. This value is even larger than without than the pure alkyne. So for this azide axis one, this diffusion of these two copper alkyne complex is keep increasing, and because it all consumed during this reaction, so it didn't return back. And for this azide axis case, the diffusion coefficient of this active complex, it keep increasing and then return back to the baseline value. It's kind of following the reaction rate. And let's see the second reactant azide and this product. So the azide reacted with this alkyne copper complex, and then it formed this triazolide complex. So this is the intermediate of the product. So with the leave of this copper catalyst, the pure product produced. So we can see this azide diffusion. It shows increase and then return back to the baseline value. And this value is larger than the control without reaction. So here it shows this boosted diffusion. And but for this product, you can see it show increase and then saturated. So this is because the intermediates of this product, and because this size is larger, so the value is smaller. And as the reaction progresses, the amount of the pure product increase. So it shows this increased tendency. And to prove that this enhancement is not caused by the temperature change, we tried two different sets of the reactant concentration. So we tried this high reactant concentration and this low reactant concentration. And we found this azide diffusion, actually the change is almost the same, like around 5%, but it showed this higher value than this control. So we think if this enhanced diffusion is caused by the heat release, so we think during the in the high reactant concentration, the heat release should be larger than this lower reactant concentration. And then the temperature change and the induced viscosity change should be more larger. And we should see more obvious change in this higher reactant concentration, but we didn't see. So we think this enhancement is not caused by the temperature change, and this diffusion change tendency is kind of following the reaction rate for this both reactant concentration. And for the alkyne axis case, so the active complex, the 2-copper alkyne, the diffusion actually also change, increase and then decrease. It's also follow this reaction rate change. So and also for this 2-copper alkyne, the diffusion change is over 20%. So it's larger than this azide change. This is because the NMR is measured an ensemble averaged diffusion of the molecule. So for this azide, there are reacted azide and the non-reacted azide. So it's an averaged value. But for this 2-copper alkyne complex, it's the real active complex, and most of them are involved in the reaction. So the change is larger than this azide. So from this result, we can say, so the intermediates we need to be considered in the reaction, but the enhanced diffusion of the azide and the active 2-copper complex is still can be observed. So people may wonder, is that all? So is that all there is? Because people also wondering, think this NMR measurement also an artifact. So when you get some surprising results, so you will double check it, right? So because it might be like a false positive. So for this boosted diffusion, we also had double checked with the microfluidic methods in our previous result. So this is the microfluidic device. So it has two innards. So one innards is added the two reactants and the tracer, and the other innards add two reactants and the catalyst and tracer. So after this mixing process, so you can observe for this catalyst, there is a gradient depends on this position. So we found during the reaction, the tracer, actually they prefer to stay at the lower catalyst concentration area. And after the reaction, there is no position dependence. So the tracer is distribute almost, the concentration is almost the same at a different position. So this is because in the during the reaction in the higher catalyst concentration, there are more increased like diffusion because there are more catalytic events. So they need a counterbalanced backflow of the solvents, like to keep a constant fluid density. So this result can also confirm those results from the NMR. So we are trying to understand the mechanism behind this boosted diffusion. So we considered several alternative explanations, like the NMR measurement artifact. So as we mentioned at the beginning, this is not the reason, and the convection problem. So this is impossible because this reaction is happened in the water, and it has no temperature, has no gas production. And we also used a convection suppressed pulse sequence. So this is not the reason, and the temperature change we have also proved is not the reason. So the underlying for this underlying mechanism for this boost diffusion is unknown yet, but we observed this boost diffusion. So the main problem here is the timescale difference. So for common sense, the chemical reaction timescale is like femtosecond. But for this molecular motion, the timescale is like microsecond scale. So that's the reason our result is so like counterintuitive to some communities. But too little is understood about the intramolecular energy flow. The vibrational energy flow can reach like dozens or hundreds of picoseconds, and for a molecule smaller than 1 nanometer, the rotational time scale actually is like sub-nanosecond. So actually there are possibilities that the energy can convert into the motion and won't be randomized by its rotational diffusion. And also they might induce some restructuring of the solvent, and we don't know this process yet. So we just observe this enhanced diffusion. And in this click reaction, because there are so many steps involved, like the electron transfer during the reduction of the copper sulfate and the intermediates and the transition states. So we don't know this process yet. So we need more experimental evidence and a good theory to reinforce our conclusions. And there are many opportunities, and we need more people to work on this. And so I'd like to conclude my talk with a sentence Lao Tzu said. So to realize you do not understand is a virtue, and not to realize that you do not understand is a defect. So in Chinese, it's 知不知上, 不知之病. So we just reported what we observed, and we are keep learning and trying to understand the underlying mechanisms. And we believe the truth will become more clear as we study more and discuss more. Finally, I'd like to say thank you to my advisor, Professor Steve Granick. He has given me so many guidance and supports. And thanks to Tian Huang for starting this interesting chemical reaction. And now she is a professor in Peking University. And thanks for Dr. Bo for the code writing. And thanks for IBS for the funding support. And yeah, thank you for your attention. And I'm happy to have any questions and comments. Thank you.
Thank you, Huang Tian. Very nice talk. Let's see if there are any questions from the audience.
Yeah.
Okay, there is a question in the chat box. You can see it.
Okay, I'll check. Why did you stop using shuffled gradients using in your other papers? It is clearly visible that diffusion coefficient differ by more than 10%. And so why we don't use the shuffled gradients, because we found there is no dependence on this gradient sequence, because we from our result and also the group 2's data, so it didn't show the dependence on the gradients. And other paper, it is clearly visible. So in the recent paper, we used the code to analyze the data. So because when you analyze the data normally we use the MasterNova software, and we choose the integrated range, the error, the peak error. And this one actually, so because it's manually choose the error, so there are more error, and also the peak will there are some shift. So if you choose in the software, it's not very accurate. And now we fix the integrated range, and so the diffusion change will be the value will be some difference. The major difference in new paper are smaller than 10% and might disappear with shuffled gradient. For the azide, yes, it's smaller than 10%. So this is because for the azide, so the NMR measurement is the diffusion coefficient is an ensemble average. So at some certain time, some of the molecule they are they are involved in the reaction, but there are some also there's more reactants. They are just they are not involved in the reaction. So is an ensemble average of the whole azide. So they didn't show very big change. But for the 2-copper-alkyne complex, that complex is the catalytically active complex. So that one, most of the complex are involved in the reaction. So they show about 20% change, the diffusion coefficient. Yeah.
Thank you,
So
answer.
yeah. Or explain more how you calculate of the intermediates which you cannot measure directly. Which parameters and which formula do you use? So we use this equation. So you can see we can measure this. So from experiment, we measured this proton 2 and proton 1, the diffusion coefficient. And we know this concentration of this 2 copper-alkyne complex. So we know the fraction of the alkyne, and use this equation. We can calculate the active complex. So this one we measured from experiment, and this one also we can measure from experiment, and the fraction we know from the concentration change. What is the real mechanism of enhanced diffusion, and how much enhanced diffusion can efficiency for propelling? So the real mechanism, so now we thought it's like the energy release from the reaction. So this energy can partly convert into the motion, but now we cannot prove this. We just from our experiments, and we just speculate this mechanism. So the energy release from the reaction, and how much this enhanced diffusion. Yeah, this is a good question, and now we don't know yet for propelling. You mean because this molecule motor, so we don't know, so we cannot see it like now we don't know if the enhanced diffusion is directional or is just like active Brownian motion or not. So I don't know how much enhanced diffusion do you notice the we found evidence for this, and I think it will change. Okay, okay, this gamma. So this exchange, so this H and D exchange for without reaction, this ratio is nearly 2. So because when we measure this intensity ratio, we use very long relaxation delay time, because this proton 1, it has a very long relaxation time. So we use very long, and then the intensity ratio is nearly 2. So we think here if there's some exchange between the H and the D, they should show some difference. I mean, it's not like near 2. So when we measure this intensity ratio, the relaxing, yeah. And this equation, sorry, I made a mistake. Yeah, thank you for reminding. Yeah. Yeah. And
more question?
More questions. So if you have more questions, you can also contact me.